Hello everyone, my name is Mehdi Akbari. I would like to present our paper results named Towards Privacy Preserving Classification as a Service for DGA Detection. This is a collaboration work between RWTH Aachen University and Fraunhofer FIT Germany, and this work is part of Horizon 2020 European project named SAPPAN. Okay, let's start with table of contents. I will start with context and motivation. I will present the evaluation setup, then the results, and finally have a short conclusion. To get a start, let's have a look at traditional botnet communication. Here, bots usually have hard-coded approaches to reach command and control servers, or simply C2 servers. They either use fixed IP addresses or fixed domain names to take control of C2 servers. But from the perspective of the attacker, these approaches have an important drawback and can be easily defended by blocking the known IP or domain. This is the reason why botnets currently rely on domain generation algorithms, or DGAs. A DGA is a pseudo-random algorithm generating various domain names from which a botnet uses a subsequence of those for querying to contact C2 servers. It means only a small subsequence of the domain grants access to C2 servers, and the rest only results in NXD response, which means a non-existent domain. These NXDs can be analyzed to detect DGA activities. However, NXDs not only generated by DGAs, but also by typing errors, misconfiguration, and DNS misuse. To separate these benign and malicious NXDs, several binary machine learning classifiers have been proposed with very high accuracy. But with one step further, some multi-class machine learning classifiers are proposed to identify DGAs that generate specific domain names in order to target better remediations. These approaches are more challenging, but still there are very promising multi-class classifiers with regards to accuracy and performance. The problems here are the real-world training data is not always available. And also, we need to think about resource-limited devices if we want to run DGA detection, for instance, on a smartphone. Then we try to propose a cloud-based solution. We think of a DGA classifier to be used as a classification as a service. In general, for a classification as a service setup, a client sends data or setup data to the cloud server to get back the prediction results. Here we can have privacy issues because domain names usually contain sensitive information. Also, the privacy of trained model usually important for the provider. In addition, in case of DGA detection, low inference latency is very crucial. Some studies show that it should be in order of some 100 microseconds. Therefore, for privacy-preserving classification as a service for DGA detection, we build privacy-preserving classifiers from existing state-of-the-art DGA detection models, then compare privacy-preserving machine learning frameworks and try to improve performance, and then discuss the feasibility of the approach for real-world development. Just as a starting point, a naive approach shows that single inference may take up to 13 minutes and have 234 gigabytes communication overhead. This is obviously not feasible. And we had a study on the models and proposed model simplification for low approximation errors and low accuracy penalty. Okay, for data sources, we use DGA archive for malicious data, and we use RWTH University Network data for benign data. Then we create a balanced data set consisting of around 1 million samples. Half of them are DGAs and half of them are benign samples. Then another step is the selection of privacy-preserving machine learning frameworks. For this regard, we studied several frameworks based on different metrics. For example, the maturity level of the frameworks, the functions they are supporting, which are important for us, and also the availability and documentation of them. For example, if they are open source or not. And we come up with a list of these 4 frameworks for further evaluations. We selected PySwift, TF encrypted, MP2ML, and Secure Q8, which utilized MPS bit libraries. And as you see here, 3 of them utilize secure multi-party computation, and only MP2ML uses both homomorphic encryption and secure multi-party computation. The number of parties is related to the protocols they are using. 3-party protocols, MPC protocols, are only available with a trusted party, and as you see here, MP2ML and Secure Q8 also supported 2-party protocols. And only MP2ML supports one-dimensional convolutional and max pooling functions, and the others only supported 2 dimensions, which means we needed to modify our models for that. Also, all these frameworks support ReLU function, and only TF encrypted and Secure Q8 support Sigmoid. Then also we needed to select the state-of-the-art DGA classifiers, as the featureless, deep learning classifiers outperform feature-based approaches for DGA detection. We select 3 deep learning based approaches: inline, NYU, and ResNet, and 1 classifier based on random forest and a support vector machine named FANCY for a comparison. Then our evaluation metrics are inference latency, communication overhead, and accuracy penalty, which means a comparison between the plain text predictions based on the DGA models and compare it to the corresponding private predictions on the privacy preserving frameworks. Also, for performance improvement, we propose some model simplifications, which are reduction of embedding dimension, removal of ReLU, and change of pooling layers from max pooling, which is a nonlinear function, to average pooling layers. So our comprehensive results are available on our paper, and I kindly invite you to take a look at them if you are interested. But I shortly present some of our results here. As you see here, the 3-party settings has a better performance with regards to inference latency, and by applying the simplification improvements, as I said, that's the cumulative improvement that we have. We even can improve that by 95% for PySwift and NYU model. And as you see in this table, the results for 2-party settings are not that promising, and even with the simplification improvement, it's still not feasible for real-world application. Here you can see the communicational overhead is also almost same as the inference latency. It's better for three-party settings and not very good for two-party settings. And as you see here, again for PySift and NYU, and also for TF encrypted and NYU, we have very good improvements. And finally here I present the accuracy penalty for different models when we apply the simplification or when we didn't have any simplification and modification. And as you see here, we present accuracy, true positive rate and false positive rate of them, and the results shows the simplification does not change that much the accuracy, true positive rate and false positive rate for many of these cases, as I shown in green. And for some of them the change is a little bit higher, and also for one of them is surprise. The false positive rate is lower for fancy when we have our simplifications. In conclusion, unmodified models are too complex for private inference of DGA use case. But we can have simplifications on the models, and we gain reduction in inference latency up to 95%. It reduces communication overhead up to 97%, and it has accuracy penalty of less than 0.17%. But with all of these improvements, future works is needed to make privacy preserving classification as a service for DGA applicable in real world use case for real-time prediction. Thank you for your attention.